Even with a fully stocked kitchen, preparing a traditional Thanksgiving dinner requires tight logistical coordination to make sure half a dozen complex dishes finish cooking at the exact same time. Now imagine trying to produce that exact same feast in exactly 2 hours, starting from completely raw ingredients, without a single standard kitchen utensil. That restriction immediately highlights how much heavy lifting our normal appliances do. Everyday tools like chef's knives and ovens are highly specialized pieces of technology designed specifically to simplify physics. Taking those tools away forces a complete shift in mindset. You can no longer follow a standard culinary recipe. You have to analyze the mechanical requirements of the task itself. Engineers call this the first principles method. It requires breaking a complex, overwhelming problem down into its absolute most basic, foundational truths. Stripping away the convenience of modern appliances reveals cooking as raw, applied science. The first physical hurdle the engineers faced was mechanical breakdown, the process of physically reducing an ingredient's surface area and volume. Without kitchen equipment, achieving this separation of mass comes down to two specific physical requirements: the application of shear force and sharp edges. To find those sharp edges, the team repurposed heavy-duty office paper cutters, using the heavy guillotine blades to precisely slice up their vegetables. For the mashing process, they bypassed sharp edges entirely and relied on heavy, blunt force, dropping massive metal blocks directly onto the sweet potatoes. This is a textbook example of material substitution. In an engineering context, the primary function of a tool completely overrides its original intended form. Mechanical breakdown does not care about a tool's culinary history or what room of the building it came from. It only cares about the physical capability to separate mass. The next hurdle was thermodynamics, which is the requirement to transfer heat in order to alter the molecular structures of the food. Facing a total lack of standard ovens or stoves, the designers immediately began scavenging the warehouse for anything capable of generating thermal output. To soften cold butter, they realized they could repurpose the flat, metallic bed of a 3D printer as a low-temperature warming plate. This diagram shows the internal structure of that 3D printer bed. It relies on a heating coil to make plastic prints adhere, but when that thermal energy radiates upward into a block of solid fat, it rapidly loses structural integrity. For tasks requiring higher energy, they escalated to laboratory-grade equipment, igniting Bunsen burners to rapidly bring large beakers of water to a rolling boil. Outside, they constructed makeshift ovens out of raw cinder blocks, designing them to capture and sustain the ambient heat from burning wood long enough to safely cook a turkey. To finish the sweet potato casserole, they abandoned the slow, sustained heat of the cinder blocks in favor of a massive burst of flame from a blowtorch, instantly searing the surface of the marshmallows. From the gentle warming of 3D printers to the extreme thermal shock of a flamethrower, these are all simply different levers controlling the exact same thermodynamic system. The final scientific category the engineers had to tackle was chemical alteration. This is the process of physically changing a food's baseline composition. This became especially difficult when making cranberry sauce, a dish that normally requires precise measuring tools and a proper stovetop production setup. By applying intense heat, they boiled the water out of the orange juice, driving volume down as steam escapes. Removing water increases the concentration of sugar molecules. As they pack together, that concentrated sweetness triggers the cranberries to burst into sauce. Similarly, when the turkey gravy refused to properly coagulate, the team dumped raw flour into the beaker, using it as a rapid chemical thickening agent to manually bind the liquid. The perfect flavor and texture profile is the measurable output of a successfully managed chemistry experiment. At the end of the strict 2-hour countdown, the engineers presented a mathematically successful meal, complete with a fully cooked turkey, pies, and an array of sides. The execution was entirely chaotic, full of vibes-based measuring and highly questionable hygiene, but the physical product on the plate was surprisingly effective. These results demonstrate that a kitchen functions as a highly specialized engineering workshop. Whether you are melting butter in a non-stick frying pan or directly on top of a 3D printer bed, the governing laws of physics remain exactly identical. The engineers successfully hacked those laws of physics to win what they assumed was a luxury Hawaiian cruise. Instead, Their prize was a literal Terry Crews action figure dressed in a Hawaiian shirt.